Yeah, that's right. Sorry. So today I'll be talking about laminar premixed flames. So premixed flames where the fuel and air. So where we will be finding these flames. So do you guys where we can find these flames? The major or the main application of having a premixed or a non-premixed flames. So do you guys have any idea about where we apply this flame theory? Any idea about that? All right, so you guys can see my screen, right? I'll start writing right now. Import injection engines. Um, no, it's not the port injection engines. It's in a gas turbine engines, right? Do you know Brighton cycle? You know Brighton cycle. So the Brighton cycle is basically compressor, combustion chamber, and a gas turbine, right? So this combustion chamber has a flame on it where the fuel and air are continuously burned and providing exhaust gases that turns the blades of the turbine. Um, so when the blades of the turbine turns around its axis, it gives you either power for the land-based utilities gas turbines, or it gives you thrust to be used in jet engines for aeroplanes or fighters. So this is basically um, where we can apply premixed flame theory or non-premixed flame theory. So do you guys know the difference between the non-premixed and premixed flame theories? So laminar premixed flames. Theory number 8. Laminar premixed flames. So the laminar premixed flames definition is where fuel and air are remixed before um, the combustion process. So how the premix takes place is um, the fuel and air introduced, or they have to travel together for a certain length until they reach out the burning point or the combustion point. So um, so the main application is gas turbine combustion chamber. gas turbine combustion chamber. So the gas turbine is basically, this is a Brayton cycle, where we having where we are having compressor and combustion chamber and a turbine. This is a gas turbine. That's a compressor, and this is a combustion chamber. Combustion chamber, and so the gas turbine is either land based utilities, is either utilities, gas turbine, or jet engines. So that this one produces power, this one produces thrust force, right? The combustion chamber, so the flame is going to be generated here. So let's assume that this is a jet flame. So this kind of one is a jet flame. All right. And also it has a stabilization mechanism and so on and so forth. So when the gas turbine, when the exhaust gas goes to the gas turbine, so the blades inside the gas turbine will be rotating, and it powers the compressor at the first stage. I think you've taken this in your thermodynamics. So and it generates power, work. All right. So here, this flame is either laminar flame or turbulent flame. All right. So no, I didn't distinguish between the premixed and non-premixed. So premixed, air plus fuel coming through here, and it's going to be burned over there, right? For the non-premixed, fuel coming from the pipe or upstream, and it mix, or it's going to be burned with the surrounding air. So the green things here is air, right? So sometimes we call it a diffusion flame. All right then. All right. So for our study today, it's going to be laminar premixed flames, and we have a very well-known premixed flame correlation called Metghalchi correlation. Metghalchi is he is the editor of an ASME journal, ASME journal, American Society of Mechanical Engineering in US. So he's the editor of this journal right now, and he identified a correlation that you can get the laminar flame speed uh, of any kind of fuel at any specific condition. So, so I'm gonna solve the first problem. And then we will be solving the Metghalchi correlation in the second problem as well, which is very straightforward. All right. So, do you guys have any questions so far up to now? All right, so we will be considering um, outward propagation of spherical laminar flame. So it's a spherical laminar flame. It's a spherical laminar flame, and it goes to infinite medium of unburned gases, right? So the flame. Let's assume that this is the flame, the spherical flame. And it has a certain mass mb. B is the burned gases, right? And this is surrounded in infinite medium of unburned gases. So the surrounding is unburned gases. So we call it the unburned gases is U unburned and B is burnt, right? So assuming that SLTU and TB are all constants, assume laminar flame speed SL. Tu is the temperature of the unburned gases. Temperature, and TB is burned gas temperature. So it's basically if we draw a side view of this. So let's say that this is like the front view. A side view of this is like you're gonna have a pipe, and this pipe has a premixed mixture of air and fuel, and it generates a spherical flame, right? So this is the flame, and the unburned gases is here. So whatever comes here through the pipe is unburned gases. It has a temperature Tu, and this has a temperature Tb. This is a burned gases temperature, and also it propagates with a SL laminar flame speed. So determine an expression for the radial velocity of the flame front for a fixed coordinate system with its origin at the center of the sphere. Use mass conservation for an integral control. So we will be driving an expression for radial velocity for the radial velocity, and use mass conservation for an integral while control volume, right? Using mass conservation. So the first thing I'm going to do is writing the mass of the burned gases of the flame. So the mass of the burned gases it's a spherical flame, so the mass is going to be rho multiplied the volume of the flame. So rho is going to be rho for the burned gases because it's the flame in a spherical shape. Volume, so rho has to be in burned because there is a difference between the burned gas density and unburned gas density because there is difference in the temperatures as well. So rho B multiplied by 4/3 the volume of a sphere by r, the radius of the flame, to the power 3. Right? So, and the mass, so this is the mass of the burned gas. The other mass is the mass of the unburned gas, right? Here. The mass of the unburned gases is rho unburned gases multiplied by volume of the volume here. So this volume is going to be from the dimensions, it's going to be rho u velocity of the flame, or the flame velocity, or the laminar flame speed, multiplied by the area of the flame. So area of the flame is sphere. So the sphere area is 4 pi r fuel or r flame square. So by doing the integral control volume, if we do an integral control volume, so this is going to be by applying the integral control volume. So we have taken our control volume over here, over the spherical flame. So this is going to d by dt of m of the burned gases is going to be d by dt of 4/3 pi rho b rf to the power 3, and it's going to be the same as the mass of the unburned gases, right? So if we do d by dt, so what is the thing? So what is the constant, or what is the parameter that is function of time here? Is the radius of the flame, because the radius of the flame is not constant with time, and this is gonna be equal to the mass of the unburned gases, because mass of unburned gases is supposed to be constant, right? So 4/3 by rho b d rf square cube over dt equal to rho u SL laminar flame speed for this thing, which is here. You're gonna get this mass over there. 4 pi RF to the square. And if we do this, 4 over 3 pi RB. If we do the differentiation of RF, it is going to be 3 RF square drf by dt is equal to rho u SL 4 by RF square. So we can cancel out flame radius pi 4 with 4, 3 with 3, and we're gonna left with drf by dt. So the change of the radius of the flame is function of rho u, rho b, and the laminar flame speed. So the dimension or the thickness of the flame is function of the density of the unburned gases and burned gases, which related to the temperature of the unburned gases and burned gases, and laminar flame speed, which is a function of the conditions and the fuel, the boundary conditions and the fuel type, right? So that this is the flame velocity or the flame propagation, which is the change of the radius with respect to time. This is the flame front velocity. And that's question number 1. Question number 2. Use Metghalchi and Keck correlation calculate the laminar flame speed. For a stoichiometric mixture. Stoichiometric mixture. So the stoichiometric mixture, from the stoichiometric, we know that phi is what? Phi is what? At a pressure of 1 atmosphere and the temperature of the unburned gas is 400 K. So the first is for propane. And second for isooctane. So when we say stoichiometric, what will be the phi, the equivalence ratio? So the equivalence ratio is the only is the operating condition for any continuous flame or any laminar flame. All right. So what is phi here in this case? Because if you remember, I don't see the chat if you're writing in the chat box. Anyone write in the chat box? Yeah, 1. Yeah, thank you. I don't know why I don't get a notification sound when someone writes something in the chat box. I don't know why. All right, so thank you. No problem. All right, so Let's start by Metghalchi correlation. The Metghalchi correlation the Metghalchi correlation So for Metghalchi correlation, it's laminar flame speed is equal to the reference laminar flame speed, which is coming from experiments, multiplied by TU, the unburned gas temperature over T reference to the power gamma, and PU, the pressure of the unburned gases, the reference pressure to the power beta, multiplied by 1 minus 2.1 Y dilution. So dilution is the amount of excess air entering the combustion chamber for cooling. All right? So dilution is the dilution air, right? It has to be given to you in exam. If it's not given, you consider it zero as zero. All right? This has to be given. And sometimes it's the secondary air of the combustion chamber. So sometimes the combustion chamber has a primary air coming with the fuel here. And the secondary air enters the combustion chamber from the sides and it cools down the combustion chamber. And we call it secondary air, right? And it enters the combustion chamber from the sides, like this. And this is the flame. All right. So SL reference is Bm plus B2 multiplied by Phi equivalence ratio minus Phi m, right? And all of these constants should be all of these constants should be obtained from the table in the lecture. Those are experimental constants. Should be obtained from this table only. Here. So where PM, V2, and Phi, depending on the fuel type, are given as here, right? So that's Phi. All depends on the type of the fuel, and Bm and B2 is our constants for the reference laminar flame speed, right? And also they are depend on the fuel type, right? So now we get BP and Phi m Now we TU is the unburned gas temperature, PU is unburned gas pressure, and alpha and beta. Alpha and beta. Alpha is function of the equivalence ratio, and beta as well is function of the equivalence ratio. Right? Sounds good. So I think all set. We can apply this correlation right now. All right. So okay. Got this. Laminar Premixed speed. We got the Laminar Premixed speed for set 1, set 2, set 3, set 4. Then okay, the air properties. Okay, so I didn't solve the second question. Well, I will solve it right now. I'm going to solve it. Okay. So sorry for that. So let's say for propane. Cool. Propane. So SL is, I wrote it again, right? SL reference, TU over T reference to the power gamma, and PU to the P reference to the power beta, and 1.2, sorry, 1 minus 1.2. To Y dilution, Y of the dilution. And knowing that the reference T reference is atmospheric, P reference is 1 atmosphere. Okay. So the solution for that SL reference is Bm plus B2 phi minus phi m to the square, and this is going to give you, for propane, Pm is 34.22, and B2 for propane is minus 138.65. Those in centimeters, as I showed to you here, those are in centimeters per second, all right? So this Pm for propane is 34.22, and for B2 is minus 138.65, and for Cm is 1.808, if you can see here, right? So and our phi is in a problem, it's 1 minus Vm, which is 1.08 all squared. So the reference laminar flame is 33.33 is going to be obviously in centimeter per second. All right, and alpha and beta. alpha is 2.18 minus 0.81 minus 1. So this is going to be 0. So this, I mean alpha and beta is going to be the first term of each one because phi is psychometric, right? So based on that, alpha is going to be 2.18 and beta is going to be minus 0.16. And if we take all of those things and substitute here, so SL 33.33, TU, which is 400 over 298 to the power gamma. Gamma is 2.18. PU 1 atmosphere, so it's going to be 1 to the power beta minus 0.16, and it's going to be 1 because there is no dilution here. So the laminar flame speed is 63.3 centimeter per second. Right, I think you can do it. It's very, very, very straightforward. You can do it for isooctane. Isooctane. Right. So the third problem is very similar to the second one, but for the third problem, he asks for the critical radius. He asks for the critical radius of ignition of a stoichiometric propane air mixtures and mixture at 1 atmosphere, right? So for the third problem, I'll show it to you here right now. I'll show it to you. So for the third problem, where's the tutorial? All right, so for the third problem here, he wants you to use the Metghalchi correlation to calculate laminar flame speed of propane for different sets, right? Which is very easy. So we just did it for multiple for propane, and you can do it for like all of these sets. And the last one for everyone here. So the pressure P over P reference was 1. But for the last one, P over P reference was 10. So he wanted you to know the effect of changing the combustion pressure on the laminar flame speed. So the effect of the laminar pressure on the flame speed. What do you guys expect? So what do you guys expect if we increase the pressure inside the combustion chamber? What will be the laminar flame speed? It will increase or decrease? What do you guys think? So if we have a combustion chamber and the flame is propagating inside the combustion chamber, a continuous flame propagation. So what you think as compared to atmospheric combustion chamber? So will the pressure, will the flame speed increase or decrease? No, it's not gonna increase. It's gonna decrease because the chamber is compressed. So the propagation for the flame inside a compressed chamber would be difficult as compared to an atmospheric pressure. So the atmosphere surrounding the flame is going to be very the atmosphere is going to be very compressed. So the propagation of the flame will be decreasing. So you can do it while studying. So you can do it while studying, and uh, you will see the difference. Um, you will see the difference. All right. Okay. So from here, from this set, you're gonna find the effect of different things. From the third problem here. Look, from the third problem here. So you're gonna find the effect of changing the pressure, changing the temperature. Like for the first one, he said he made the pressure is constant for 3 sets and changed it for one. And for the second set, he made the temperature constant for 3 sets and changed it for the second set. And for the third one, he changed it like he kept the equivalence ratio constant and he changed it for the third one, right? So basically from here you're gonna get overview on the effect of the pressure, unburned gas temperature, or the combustion or the flame temperature, and equivalence ratio on the laminar flame speed. And for the critical radius for ignition of a stoichiometric propane air mixture, so the critical radius is very simple. If you want to get the critical radius, there is just one equation for obtaining the critical radius. For R critical. All right, so R critical is by definition, R critical is the square root of 6 alpha over the laminar flame speed. So alpha here is the thermal diffusivity. Alpha is the thermal diffusivity, which is the ratio between K over rho Cp. So obviously rho of the unburned gas. All right. So this K and the Cp, K and Cp has to be obtained at the average temperature, right? So this K is the thermal conductivity. And Cp is the specific heat at constant pressure. Cp is specific heat. Right. And T bar is the average temperature between the burned gases and unburned gases. Tp over T over 2. Tu is like let's say the temperature, the unburned gas temperature 300, 298. Just assume, like this is not the solution of the third problem, but it's just gonna give you, like assume that the burned gas temperature was 2000 Kelvin over 2. So this is gonna give you an average temperature, and you're gonna use this temperature, look at the air properties from T average, look up air properties, add T average, and get K and get Cp at T average, but get the unburned gas temperature at what temperature? At 300. 300 Kelvin. So this is going to be 2300 over 2. 2300 over 2 is around 11. Right. So just look up the air properties. Look up the air properties at 1150 Kelvin at 1150 Kelvin, and from here you're gonna get K and CP and rho U. And when you get the thermal diffusivity, so you can get the thermal diffusivity alpha. And once you get the thermal diffusivity and you have the laminar flame speed at each condition or at each set of the previous problem, you're going to get the R critical for each of the operating conditions. Then you get the critical radius. So we get the critical radius because we wanted to know it will affect, obviously it will affect the dimension of the combustion chamber that has to accommodate this propagating flame. And that's all for today's tutorial. So you guys have any questions? I hope that was clear. Was that clear? All right, sounds good. Amazing. So I just have a request for you guys. Just one request. I just need you to fill out the evaluation because I like to know your ideas about the tutorial and my style and things you like, things you don't like, ideas to improve, and anything you felt good about, right? So this is my only request from you during that semester. So you just go do your evaluation and be honest, and that's it. This is what I'm asking you, just asking you to do. All right? How many of you who will write an evaluation? It's okay. You don't have to say I know. Oh, thank you. No problems at all. So I just need a feedback. I get very happy when I receive feedback. Um, um, just be honest and like just write things you like, things you don't like, and things you recommend to improve. That's good. All right. Thank you so much. Thank you so much. All right. So if you guys don't have any questions, all right. I'll see you next time. Take care. Bye bye. Thank you, Brian. Thank you.